Lieutenant Hans Weber watched in disbelief as his wingman's Messerschmitt Bf-109 simply vanished in a brilliant orange flash, the explosion occurring nowhere near where the American flak shells should have detonated. Something was terribly wrong with the enemy's anti-aircraft fire, something that defied everything he knew about aerial combat. The Americans had somehow made their guns impossibly accurate, and German pilots were dying at unprecedented rates. What Weber didn't know was that he was witnessing the debut of one of the war's most closely guarded secrets, a tiny electronic marvel that would revolutionize warfare forever. Before we carry on, please hit the subscribe button to make my day, and let me know where you are watching from in the comments. The story begins, not in the skies over Europe, but in the sterile laboratories of Johns Hopkins University's Applied Physics Laboratory in 1941, where Dr. Merle Tuve stared at a problem that had plagued military commanders since the invention of anti-aircraft artillery. Traditional flak shells relied on timed fuses, preset to explode at specific altitudes based on calculations of enemy aircraft speed, distance, and trajectory. Even with perfect calculations, which rarely occurred in the chaos of battle, shells often exploded harmlessly in empty air, while enemy bombers continued their deadly missions unscathed. Tuve, a brilliant physicist with an analytical mind and an understanding of radio wave propagation, had been wrestling with this challenge for months when inspiration struck during a late-night session reviewing radar technology. If radar waves could detect aircraft at great distances, why couldn't similar technology be miniaturized and packed into artillery shells to detect nearby targets and trigger detonation at the optimal moment? The concept seemed almost impossibly ambitious, requiring the creation of a radio transmitter, receiver, and detonation circuit small enough to fit inside a 5-inch artillery shell, while robust enough to survive the tremendous forces of being fired from a gun. The technical challenges seemed insurmountable to most engineers, but Tuve assembled a team of the nation's brightest minds, including Dr. Ralph Baldwin, an astronomer whose understanding of celestial mechanics proved invaluable in calculating trajectory mathematics, and Dr. Alexander Ellett, whose expertise in vacuum tube miniaturization would prove crucial to the project's success. Working in conditions of absolute secrecy, with security measures rivaling those of the Manhattan Project, the team began the painstaking process of creating what would eventually be known as the variable time or SEPL VT proximity fuse. The first prototypes were crude affairs, barely functional devices that often failed to survive the shock of firing or proved too sensitive, detonating prematurely or not at all. Baldwin spent countless hours hunched over workbenches, adjusting circuit designs, and testing vacuum tubes no larger than a man's thumb, each one hand-crafted with precision that would make Swiss watchmakers envious. The radio frequency had to be carefully calibrated to avoid interference from other electronic equipment, while maintaining sensitivity to detect aircraft at distances between 20 and 100 feet, the optimal range for maximum fragment effectiveness. Meanwhile, across the Atlantic, German flak crews were becoming increasingly frustrated with their inability to bring down Allied bombers with consistent effectiveness. Hauptmann Klaus Richter commanded a battery of 88mm guns, defending the vital ball-bearing factories in Schweinfurt. Watching helplessly as formations of American B-17 flying fortresses rumbled overhead day after day, their crews seemingly oblivious to the thousands of shells bursting around them. Traditional flak tactics required gunners to estimate aircraft altitude, speed, and direction, then set mechanical time fuses accordingly, hoping their calculations would place explosive shells in the right location at precisely the right moment. Richter had trained his crews to perfection, their movements choreographed with military precision as they loaded, aimed, and fired their weapons in steady rhythm. But even the most experienced gunners achieved hit rates barely exceeding 5%. Most shells exploded uselessly in empty sky, their fragments scattered harmlessly away from intended targets, while precious ammunition and time were wasted in futile barrages that served primarily to boost crew morale rather than inflict meaningful damage on enemy aircraft. Back in Maryland, Tuve's team achieved their first breakthrough in early 1942, when they successfully created a vacuum tube capable of withstanding the massive acceleration forces encountered during firing while maintaining Brel. Electrical functionality. The tube, barely 2 inches long and containing components measured in thousandths of inches, incorporated a radio transmitter operating at 180 MHz, a frequency chosen to minimize atmospheric interference while maximizing target detection capability. The receiver circuit was equally sophisticated, designed to detect reflected radio waves and trigger detonation when signal strength indicated optimal proximity to enemy aircraft. Testing proved to be another enormous challenge, requiring the construction of specialized facilities where prototype fuses could be fired safely while their performance was monitored and analyzed. Dr. Baldwin supervised these tests personally, often spending entire days at proving grounds watching shells explode against stationary targets, mobile drones, and eventually live aircraft piloted by volunteer test pilots who demonstrated remarkable courage flying predetermined patterns while experimental munitions burst around their aircraft. The first successful test occurred on August 23, 1942, when a 5-inch shell equipped with a VT fuse detonated 18 feet from a radio-controlled target drone, destroying it completely with fragment patterns that would have been impossible to achieve with conventional timed fuses. The euphoria in Toothey's laboratory was tempered by the realization that perfecting the technology would require months of additional development, testing, and production scaling before the fuses could be deployed in combat situations. Production presented its own set of seemingly impossible challenges, as each fuse contained over 300 individual components, all of which had to be manufactured to tolerances measured in thousandths of inches while maintaining absolute reliability under combat conditions. The General Electric Company was contracted to establish production facilities, ultimately building an entire factory dedicated exclusively to VT fuse manufacturing, employing thousands of workers who had no idea what they were creating beyond knowing it was vital to the war effort. Security surrounding the project was unprecedented, with workers required to sign multiple oath documents and submit to extensive background investigations before being permitted access to production areas. Even component suppliers were kept ignorant of their product's ultimate purpose, receiving specifications for vacuum tubes, circuit boards, and mechanical assemblies without understanding how these parts would be integrated into finished weapon systems. By late 1943, production had reached sufficient levels to begin limited combat deployment, but military commanders faced another dilemma regarding when and where to introduce this revolutionary technology. Using VT fuses prematurely could compromise their secrecy if unexploded shells fell into enemy hands and were reverse-engineered by German scientists, potentially negating the Allies' technological advantage. Conversely, waiting too long meant allowing unnecessary casualties among Allied aircrews who could benefit from improved anti-aircraft protection. The decision was made to debut VT fuses in the Pacific Theater, where the likelihood of unexploded shells falling into Japanese hands was considered minimal due to the naval nature of most engagements. American destroyers and cruisers began equipping their 5-inch guns with proximity-fused ammunition in December 1943, and the results exceeded even optimistic projections. Japanese kamikaze attacks, which had proven devastatingly effective against conventionally armed ships, suddenly began failing as suicide pilots found themselves flying into walls of precisely timed explosions that destroyed their aircraft before they could reach their targets. Admiral William Halsey, commanding the Third Fleet, reported to Washington that VT-fused anti-aircraft fire was proving 10 times more effective than conventional ammunition, with single shells often destroying multiple attacking aircraft simultaneously as proximity-triggered explosions created overlapping fragment patterns that covered vast areas of sky. Japanese pilots, accustomed to diving through predictable flak patterns, found themselves facing an entirely new type of defensive fire that seemed to anticipate their every maneuver. In Europe, German intelligence services began receiving disturbing reports from Luftwaffe pilots describing inexplicably accurate Allied anti-aircraft fire that defied conventional understanding of flak effectiveness. Lieutenant Weber, flying combat missions over Normandy following the D-Day landings, submitted detailed reports describing shells that seemed to explode with supernatural precision, always at the exact moment and location needed to inflict maximum damage on German aircraft. Weber's squadron had lost 12 planes in 2 weeks, an attrition rate that would have been considered catastrophic even during the worst periods of the Battle of Britain. But these losses were occurring during routine reconnaissance missions, rather than major combat operations. Enemy flak, previously regarded as a manageable hazard that skilled pilots could evade through tactical maneuvering, had somehow transformed into a deadly precise weapon system that claimed victims with mechanical efficiency. German military engineers, desperate to understand this new Allied capability, began collecting unexploded shell fragments from crash sites and bombing targets, searching for clues that might explain the dramatic improvement in enemy anti-aircraft effectiveness. Initial investigations proved frustrating, as most proximity-fused shells detonated completely, leaving few intact components for analysis. And those fragments that were recovered appeared to contain unfamiliar electronic equipment unlike anything in German arsenals. Dr. Heinrich Gottwald, Germany's leading expert on radar and radio technology, was assigned to investigate these mysterious shell components in a laboratory facility outside Berlin. Gottwald had previously worked on Germany's own radar development programs and possessed intimate knowledge of electronic warfare capabilities, making him uniquely qualified to analyze captured Allied equipment. However, the fragments he received were so badly damaged by explosions that reconstructing their original configuration proved nearly impossible. What Gottwald could determine was deeply troubling from a German perspective, as the fragments clearly contained sophisticated radio equipment far smaller and more advanced than anything German industry had achieved. The vacuum tubes, when intact enough for examination, displayed manufacturing techniques and miniaturization levels that suggested the Allies had made significant breakthroughs in electronic technology, while Germany had focused primarily on conventional weapons systems. Meanwhile, Allied bomber crews began reporting dramatic changes in German fighter tactics, as Luftwaffe pilots adapted to the new reality of proximity-fused anti-aircraft fire. Squadron leader James Morrison, piloting a B-24 Liberator on missions over German industrial targets, noticed that enemy fighters were increasingly reluctant to press attacks through friendly flak zones, apparently having learned through bitter experience that Allied anti-aircraft fire had become exponentially more dangerous. Morrison's bomber group, the 392nd Bomb Group, had previously suffered heavy losses to German fighters that exploited gaps in Allied fighter escort coverage, diving through flak fields to attack bomber formations with relative impunity. However, by summer 1944, these tactics had largely ceased, as German pilots discovered that flying through Allied anti-aircraft fire meant almost certain death rather than nearly calculated risk. The psychological impact on German aircrew proved as significant as the physical destruction caused by VT fuses. As pilots who had previously relied on skill and experience to navigate flak fields found themselves facing weapons that seemed to possess almost supernatural accuracy. Combat reports submitted to Luftwaffe headquarters described shells that knew when aircraft were nearby, exploding at precisely the right moment, regardless of pilot evasive maneuvers or aircraft performance. Characteristics. Dr. Gottwald's investigation finally achieved a breakthrough in September 1944 when his team recovered a relatively intact VT fuse from a crashed American bomber that had been shot down over Bavaria. The fuse had failed to detonate due to damage sustained during the aircraft's crash, providing German scientists with their first complete example of Allied proximity technology for detailed analysis. Examining the device under powerful microscopes, Gottwald's team discovered an ingeniously compact radio system containing a transmitter, receiver, and detonation circuit integrated into a package smaller than a cigarette pack. The vacuum tubes were unlike anything in German inventories, utilizing manufacturing techniques that suggested the Allies had invested enormous resources into miniaturization research, while Germany had focused on producing larger quantities of conventional equipment. The revelation that Allied scientists had successfully created reliable proximity fuses sent shockwaves through German military leadership, as it demonstrated a level of technological sophistication that Germany could not match with existing industrial capabilities. Attempts to reverse engineer the captured fuses proved futile, as German manufacturing facilities lacked the precision equipment and specialized materials needed to replicate American vacuum tube technology. General Adolf Galland, commanding the Luftwaffe fighter forces, received Gottwald's technical report with growing alarm as he realized the full implications of Allied proximity fuse technology. German fighters, already outnumbered and increasingly short of experienced pilots, now faced anti-aircraft defenses that had been dramatically enhanced through scientific innovation, creating an additional layer of danger that skilled airmanship alone could not overcome. Galland immediately ordered changes in fighter tactics, forbidding pilots from attacking Allied bomber formations when friendly flak was active, and mandating new approach patterns designed to minimize exposure to proximity-fused anti-aircraft fire. However, these tactical modifications severely limited German fighter effectiveness, as bombers could often reach their targets without meaningful interceptor opposition simply by flying routes covered by their own BAF. Anti-aircraft weapons. The introduction of VT fuses in European ground combat came during the Battle of the Bulge in December 1944, when General George Patton's Third Army faced desperate German infantry attacks across the frozen Ardennes region. Patton, known for his aggressive tactics and innovative use of technology, immediately recognized the potential for proximity-fused artillery shells to devastate enemy troops advancing across open terrain. Traditional artillery tactics required precise timing to achieve effective airburst patterns above enemy positions, with gunners calculating complex mathematical formulas to determine proper fuse settings based on range, weather conditions, and target elevation. Even experienced artillery crews achieved limited effectiveness with conventional airburst techniques, as slight miscalculations resulted in shells exploding too high, too low, or completely missing target areas. VT-fused artillery shells eliminated these calculation requirements, automatically detonating at optimal heights above German positions, regardless of terrain variations or atmospheric conditions. The first combat use occurred on December 22, 1944, when American artillery batteries targeted German infantry positions near Bastogne, using 105 mm Askeen howitzers loaded with proximity-fused ammunition. The results were immediate and devastating, with shells exploding precisely 20 to 30 feet above German trenches and creating fragment patterns that covered enormous areas with lethal steel fragments. German soldiers, accustomed to taking cover in foxholes and trenches that provided excellent protection against conventional artillery, found themselves completely vulnerable to overhead explosions that showered fragments directly into their positions. Captain Wilhelm Hoffmann, commanding a company of German infantry near Bastogne, watched in horror as American artillery shells began exploding above his positions with uncanny precision, creating a steel rain that penetrated even the deepest foxholes and strongest defensive positions. His company, veteran troops who had survived years of combat on the Russian front, suffered 60% casualties within the first 10 minutes of the American barrage, an attrition rate that exceeded anything they had experienced during the bloodiest battles of the Eastern Campaign. Hoffmann submitted frantic radio reports to his regimental headquarters, describing American artillery that seemed capable of seeing through camouflage and terrain features, always exploding at exactly the right height to maximize casualties among his troops. The psychological effect proved as damaging as the physical destruction, as German soldiers began to believe that American gunners possessed supernatural abilities or advanced targeting systems that made traditional defensive tactics obsolete. American artillery crews, initially skeptical about the effectiveness of these new, secret shells, quickly became enthusiastic converts as they witnessed the dramatic improvement in their weapons' destructive capability. Battery Commander Major Robert Kane, directing fire missions with the 9th Armored Division, reported that VT-fused shells were achieving casualty rates 5 times higher than conventional ammunition, while requiring significantly fewer rounds to neutralize enemy positions. Kane's battery had previously expended hundreds of shells to achieve effects that proximity-fused ammunition accomplished with dozens of rounds, dramatically reducing ammunition consumption while increasing tactical effectiveness. This efficiency improvement proved crucial during the Battle of the Bulge, when ammunition supplies were limited due to weather conditions that prevented resupply operations. making every shell critically important to brass. Defensive success. The German offensive in the Ardennes, conceived as a desperate gamble to split Allied forces and force a negotiated peace, began to collapse under the unprecedented effectiveness of American proximity-fused artillery. German infantry attacks, traditionally effective due to superior training and tactical experience, found themselves facing defensive fire that negated their advantages through technological superiority rather than military skill. General Hasso von Manteuffel, commanding the 5th Panzer Army during the German offensive, received increasingly desperate reports from his subordinate commanders describing American artillery effectiveness that exceeded anything encountered during years of combat on multiple fronts. Manteuffel, a veteran of tank warfare who understood the importance of technological advantages, realized that his forces were facing weapon systems that fundamentally changed the nature of battlefield dynamics. Manteuffel's tactical reports, submitted to German High Command, described American artillery that seemed to possess magical accuracy, always exploding at precisely the right moment and location to inflict maximum casualties on German forces. These reports, initially dismissed by senior commanders as exaggeration or combat stress, began to accumulate into an undeniable pattern of American technological superiority that Germany could not counter with existing capabilities. By January 1945, German intelligence services had compiled sufficient evidence to conclude that the Allies had developed revolutionary proximity-fused technology that represented a fundamental advancement in weapons effectiveness. However, this realization came too late to influence German strategy, as the nation's industrial capacity had been devastated by continuous bombing campaigns and resource shortages that prevented development of counter-technologies. The proximity fuse, originally conceived as a solution to anti-aircraft accuracy problems, had evolved into a war-winning technology that provided the Allies with decisive advantages in both air and ground combat situations. American and British forces, equipped with VT-fused ammunition, could engage enemy targets with precision and effectiveness that seemed almost supernatural to opponents who lacked understanding of the underlying technology. Dr. Tuve, working in his Maryland laboratory, received reports of VT-fused combat effectiveness, with satisfaction tempered by the knowledge that his invention was contributing to massive casualties on both sides of the conflict. The physicist, who had entered the project with purely scientific motivations, found himself grappling with the moral implications of creating weapons technology that killed with unprecedented efficiency. However, Tuve also understood that his work was shortening the war by providing Allied forces with decisive technological advantages that accelerated German defeat while potentially saving lives on both sides through quicker conflict resolution. The proximity fuse, like many wartime innovations, represented the complex intersection of scientific achievement and military necessity that characterized the Second World War's technological revolution. German attempts to develop counter-technologies proved futile due to industrial limitations and resource constraints that prevented the sophisticated manufacturing processes required for miniaturized electronics. German scientists, despite possessing theoretical knowledge comparable to their Allied counterparts, lacked access to the specialized materials and precision equipment needed to create reliable proximity fuse systems within the timeframe required for military effectiveness. The war's conclusion in May 1945 found German forces completely unable to counter Allied proximity fuse technology, having suffered enormous casualties from weapon systems that seemed to anticipate their every tactical maneuver. American and British commanders, initially skeptical about claims regarding VT fuse effectiveness, became enthusiastic advocates for the technology after witnessing its dramatic impact on combat operations. Post-war analysis revealed that proximity fuses had increased Allied anti-aircraft effectiveness by over 1,000%, while improving artillery accuracy to levels previously considered impossible with conventional weapons systems. The technology, developed in absolute secrecy by a small team of dedicated scientists, had fundamentally altered the balance of military power, and contributed significantly to Allied victory in both European and Pacific theaters. Lieutenant Weber, one of the few German pilots to survive extended combat against proximity-fused anti-aircraft fire, submitted detailed post-war reports describing the psychological impact of facing weapons that seemed to possess supernatural accuracy. Weber's accounts, along with testimonies from other German veterans, provided Allied intelligence services with valuable insights into the effectiveness of technological superiority as a force multiplier in BS. Modern warfare. The proximity fuse's legacy extended far beyond its wartime applications. As the miniaturization techniques and electronic systems developed for VT fuses became foundational technologies for post-war advances in radar, television, and eventually computer systems. Dr. Tuve's team, originally focused on solving a specific military problem, had inadvertently created technologies that would transform civilian society in ways they could never have anticipated. Captain Hoffman, surviving the war despite suffering severe wounds from VTF-used artillery during the Battle of the Bulge, later reflected on the profound impact of facing weapons that rendered traditional military tactics obsolete through technological innovation. Hoffman's memoir, published in the 1960s, provided civilian readers with insights into the soldier's perspective when confronted with enemy capabilities that exceeded understanding and defensive possibilities. The story of the proximity fuse represents one of the Second World War's most significant but least understood technological achievements, demonstrating how scientific innovation could provide decisive military advantages when combined with adequate resources and strategic vision. The small team of American scientists, working in conditions of absolute secrecy, had created a weapon system that fundamentally altered the nature of aerial and ground combat while contributing substantially to Allied victory. Major Kane, commanding American artillery equipped with proximity fuses, submitted extensive post-war reports documenting the dramatic improvement in his battery's effectiveness when VT fused. Ammunition became available. Kane's analysis, distributed throughout the American military establishment, helped establish proximity fuse technology as a standard component of post-war artillery systems, and influenced tactical doctrine development for decades following the conflict's conclusion. The German experience with Allied proximity fuses illustrated the crucial importance of technological research and development in modern warfare. As nations that failed to invest adequately in scientific innovation found themselves facing enemy capabilities that could not be countered through traditional military methods. The proximity fuse, like radar and other wartime technologies, demonstrated that scientific superiority could provide decisive advantages that skilled leadership and tactical expertise alone could not overcome. Dr. Gottwald's post-war career included extensive work developing German electronics industries, drawing upon knowledge gained from analyzing captured Allied proximity fuses while contributing, to his nation's eventual technological recovery. Gottwald's experience analyzing VT fuse technology provided him with insights into miniaturization techniques and precision manufacturing methods that proved valuable in civilian applications, ranging from radio equipment to early computer systems. General Galland, reflecting on the Luftwaffe's experience facing proximity-fused anti-aircraft fire, acknowledged that German aviation forces had been confronted with weapons technology that fundamentally changed aerial combat dynamics in ways that traditional fighter tactics could not address. Galland's post-war writings emphasized the importance of technological development in maintaining military effectiveness, lessons that influenced German rearmament policies during the Cold War period. The proximity fuse's development and deployment represented a triumph of American scientific and industrial capabilities, demonstrating that democratic societies could mobilize intellectual resources effectively when facing existential threats. The project's success relied upon close cooperation between academic researchers, government agencies, and private industry, creating organizational models that influenced post-war science and technology policy development. General Manteuffel's tactical reports, declassified decades after the war's conclusion, provided military historians with detailed documentation of German perspectives when facing technologically superior Allied forces equipped with proximity-fused weapons systems. Monteufel's analysis emphasized the psychological impact of confronting enemy capabilities that seemed to violate understood principles of military science, creating doubt and uncertainty among German commanders who had previously relied upon tactical expertise and combat experience. The story concludes with the recognition that the proximity fuse represented far more than a simple weapons improvement, instead constituting a fundamental advance in military technology that changed warfare permanently while contributing to broader technological developments that transformed post-war society. The small team of scientists working in Maryland laboratories had created not merely a better fuse, but had demonstrated the decisive importance of scientific innovation in modern conflict while establishing technological precedents that continue influencing military and civilian applications today. The legacy of the proximity fuse extends beyond its immediate wartime impact, serving as an example of how targeted scientific research, combined with adequate resources and strategic vision, could produce revolutionary advances that provided decisive advantages in military competition. The technology that began as a solution to anti-aircraft accuracy problems evolved into a war-winning capability that fundamentally altered the balance of power between Allied and Axis forces while contributing to scientific knowledge that benefited post-war technological development across numerous civilian applications. Lieutenant Weber's final report, submitted after Germany's surrender, acknowledged that Luftwaffe pilots had been facing weapons technology that exceeded their understanding and defensive capabilities, creating combat conditions where skill and experience proved insufficient to overcome enemy technological advantages. Weber's testimony, along with accounts from other German veterans, provided Allied analysts with confirmation that proximity fuse technology had achieved its intended strategic objectives while demonstrating the profound impact of scientific superiority on military operations. The development of the proximity fuse had required overcoming challenges that extended far beyond the laboratory, creating an entire industrial ecosystem dedicated to producing these revolutionary devices under conditions of absolute wartime secrecy. The General Electric facility in Cleveland, Ohio, became the epicenter of VT fuse production, employing over 15,000 workers who manufactured components without understanding their ultimate purpose or strategic significance to the war effort. Dorothy Chen, a young engineer recruited from MIT to supervise vacuum tube production, found herself managing assembly lines where workers handcrafted electronic components with precision that exceeded peacetime commercial standards while working under security restrictions that prevented them from discussing their work with family members or friends. Chen's daily routine involved inspecting thousands of miniature vacuum tubes, each one tested individually to ensure reliability under the extreme conditions of artillery firing and aerial combat. The manufacturing process required innovations in production techniques that had never been attempted at such scale, as traditional electronics manufacturing methods proved inadequate for creating components capable of surviving the tremendous acceleration forces encountered when shells were fired from naval guns or field artillery pieces. Chen's team developed new assembly procedures, using specialized adhesives, reinforced filament designs, and shock-resistant mounting systems that could maintain electrical functionality despite experiencing forces equivalent to being dropped from skyscrapers. Quality control became a matter of life and death, as malfunctioning proximity fuses could endanger friendly aircraft or fail to detonate against enemy targets at critical moments. Every fuse underwent multiple testing procedures, including vibration tests that simulated firing conditions, electrical performance evaluations under extreme temperatures, and radio frequency verification to ensure proper target detection capabilities. The rejection rate during early production exceeded 30%, requiring constant refinement of manufacturing procedures and worker training programs. Meanwhile, in the Pacific Theater, Admiral Chester Nimitz was receiving reports that vindicated his decision to deploy VT fuses against Japanese kamikaze attacks, despite concerns about maintaining technological secrecy. The USS Missouri, equipped with proximity-fused 5-inch guns, had successfully defended itself against coordinated suicide attacks that would have previously caused severe damage or complete destruction of the battleship. Commander Frank Richardson, serving as gunnery officer aboard the Missouri, witnessed firsthand the dramatic improvement in defensive capabilities when his ship faced a massive kamikaze assault during operations near Barrage, Okinawa. Traditional anti-aircraft fire had required gunners to estimate target speed and direction, then adjust their aim while hoping timed fuses would detonate shells at the proper moment to intercept incoming aircraft. With proximity fuses, Richardson's gun crews could focus entirely on tracking targets, while the shells automatically detonated at optimal range, creating overlapping fragment patterns that formed nearly impenetrable defensive barriers around the ship. Japanese pilots, accustomed to penetrating Allied defensive fire through skilled maneuvering and determination, found themselves flying into explosions that seemed to anticipate their exact flight paths with supernatural precision. The psychological impact on Japanese aircrews proved as devastating as the physical destruction caused by VT-fused ammunition, as pilots began reporting that American ships possessed magic shells that could not be evaded through conventional tactics. These reports, initially dismissed by Japanese commanders as combat stress or propaganda, began accumulating into undeniable evidence that the Americans had developed revolutionary weapons technology. Captain Saburo Yamamoto, one of Japan's most experienced kamikaze coordinators, studied attack reports submitted by surviving pilots and concluded that American anti-aircraft effectiveness had increased by orders of magnitude beyond what could be explained by improved gunnery training or tactical modifications. Yamamoto's analysis, submitted to Imperial Navy headquarters, warned that traditional kamikaze tactics had become essentially suicidal missions with minimal probability of success against ships equipped with proximity-fused ammunition. The strategic implications extended beyond individual ship defenses, as American fleet formations could now operate in waters previously considered too dangerous due to concentrated Japanese air attacks. Admiral Raymond Spruance, commanding Task Force 58, reported that his carrier groups could maintain offensive operations in areas where Japanese land-based aircraft had previously forced tactical withdrawals, fundamentally altering the strategic balance in the Pacific campaign. Back in Europe, the effectiveness of VT-fused artillery during the Battle of the Bulge had prompted rapid deployment throughout American and British ground forces, with proximity fuses becoming standard ammunition for all major artillery units by early 1945. The psychological impact on German forces proved as significant as the tactical advantages, as enemy soldiers began exhibiting signs of combat stress and unit cohesion breakdown when subjected to proximity-fused artillery barrages. Sergeant Johann Kruger, a veteran of the Russian front serving with the Wehrmacht's 7th Army in the Rhineland, described the terror of facing American artillery that seemed capable of seeing through camouflage and terrain features. Kruger's company had survived years of combat against Soviet forces, but the precision of American proximity-fused shells created conditions where traditional defensive tactics provided no protection against overhead explosions that penetrated the deepest bunkers and strongest fortifications. Kruger's combat diary, recovered after the war, documented the gradual breakdown of unit morale as German soldiers realized they were facing weapons technology that rendered their training and experience obsolete. The psychological warfare aspect of proximity fuses proved as valuable as their tactical effectiveness, as German forces began surrendering rather than face artillery barrages they considered impossible to survive. The intelligence war surrounding proximity fuses intensified as German scientific services desperately attempted to understand and counter Allied technological advantages. Professor Ernst Weber, Germany's leading electronics expert, was assigned to lead a crash program aimed at developing German proximity fuse technology based on captured Allied components and combat intelligence gathered from battlefield reports. Weber's team, working in underground facilities near Nordhausen, possessed theoretical knowledge comparable to their American counterparts, but lacked access to the precision manufacturing equipment and specialized materials needed for miniaturized electronics production. German industry, devastated by continuous bombing campaigns and resource shortages, could not provide the infrastructure necessary for proximity fuse development within timeframes required for Military effectiveness. The captured American fuses revealed manufacturing techniques that German industry could not replicate, including vacuum tube designs that required precision machinery unavailable in wartime Germany, and specialized materials that had been stockpiled by American manufacturers before the war began. Weber's analysis concluded that Germany would require at least 2 years of intensive development and industrial reconstruction to achieve proximity fuse capabilities comparable to existing American systems. However, Weber's research did provide German forces with tactical intelligence about proximity fuse limitations and potential countermeasures, leading to modifications in aircraft design and flight procedures intended to minimize vulnerability to VTF-used anti-aircraft fire. These defensive measures proved only marginally effective, as proximity fuses operated across broad frequency ranges and detection patterns that were difficult to jam or evade using available German Baran technology. Dr. Tuvey's original team in Maryland had anticipated German attempts at countermeasures, incorporating multiple backup systems and frequency diversity into VT fuse designs that made them resistant to electronic jamming or tactical countermeasures. The fuses operated using spread spectrum techniques that automatically adjusted radio frequencies to maintain target detection capability despite enemy interference attempts, demonstrating sophisticated engineering that exceeded German electronic warfare capabilities. The production challenges at General Electric required constant innovation in manufacturing techniques, as demand for proximity fuses grew exponentially throughout 1944 and early Dublin, 1945. Dorothy Chen's engineering team developed automated assembly procedures that increased production rates while maintaining quality standards, ultimately achieving daily output rates that exceeded original BIA projections by several 100%. Workers in the Cleveland facility, sworn to secrecy about their activities, developed strong camaraderie based on their shared knowledge that their work was contributing to something vitally important to the war effort, even though they remained ignorant of specific applications for their products. The security measures created a unique industrial culture where employees took extraordinary pride in their craftsmanship while accepting restrictions on their personal freedoms that would have been inconceivable during peacetime. The success of proximity fuses in both Pacific and European theaters led to expanded applications beyond anti-aircraft and artillery roles, including development of specialized versions for rocket systems, naval guns, and experimental guided missile programs. Dr. Baldwin's team began designing VT fuses optimized for different combat scenarios, including underwater proximity mines and air-to-air missile systems that would become standard equipment during post-war military development. The technological spillover effects proved as significant as immediate military applications. As techniques developed for proximity fuse production influenced post-war consumer electronics industries, television manufacturing, and early computer development, the precision manufacturing methods created for vacuum tube production became foundational technologies for the electronics revolution that transformed American society during the 1950s and '60s. Commander Richardson's experience aboard the Missouri led to comprehensive tactical doctrine revisions that incorporated proximity-fused weapons into standard naval defensive procedures, ensuring that post-war American naval forces maintained overwhelming advantages in anti-aircraft capabilities. Richardson's tactical reports, distributed throughout the Navy Department, established proximity fuses as essential components of future fleet defense systems, while influencing ship design and crew wall training programs. The cost of proximity fuse development, ultimately exceeding $1 billion in wartime expenditures, represented one of the largest scientific investments in American history, comparable to the Manhattan Project in scope and strategic significance. However, the return on investment proved enormous, as VT fuses contributed to shortened conflict duration, while saving countless Allied lives through improved defensive capabilities and more effective offensive operations. German attempts to develop alternative technologies focused on improving conventional anti-aircraft systems and creating new fighter tactics designed to minimize exposure to proximity-fused defensive fire. However, these efforts proved inadequate against the comprehensive technological advantage provided by American proximity fuse systems, which continued evolving throughout the war to counter German adaptive measures. The industrial espionage war surrounding proximity fuses involved sophisticated German intelligence operations aimed at penetrating American production facilities and research laboratories. But comprehensive security measures prevented significant technology transfer while maintaining absolute secrecy about VT fuse capabilities and limitations. German agents, despite extraordinary efforts, obtained only fragmentary information that proved insufficient for developing effective countermeasures or competing technologies. Captain Yamamoto's analysis of kamikaze effectiveness against proximity fuse defenses led to tactical modifications that achieved marginal improvements in attack success rates. But these measures required enormous sacrifices in pilot training and aircraft resources, while producing results that remained far below pre-VT fuse effectiveness levels. Japanese military leadership, facing overwhelming American technological superiority, began considering desperate measures including biological and chemical weapons as potential equalizers. The ethical implications of proximity fuse technology generated extensive debate among American scientists and military leaders, as the weapons dramatically increased casualty rates while potentially shortening overall conflict duration. Dr. Tuve wrestled with moral questions about creating technologies that killed with unprecedented efficiency, ultimately concluding that his work served humanitarian purposes by accelerating enemy defeat and reducing total war casualties on both sides. The post-war analysis revealed that proximity fuses had fundamentally altered the strategic balance between offensive and defensive capabilities, making aircraft and infantry formations far more vulnerable to ground-based defensive systems while providing enormous advantages to forces equipped with VTF-used weapons. Military strategists recognized that future conflicts would require completely new tactical approaches that accounted for the revolutionary effectiveness of proximity-triggered weapon systems. Sergeant Kruger's survival of multiple proximity-fused artillery barrages provided German intelligence services with detailed first-hand accounts of VT fuse effectiveness from the receiving end, contributing to post-war understanding of how these weapons influenced battlefield psychology and unit cohesion. Kruger's testimony documented the profound demoralization experienced by German forces when facing weapons that seemed to possess supernatural accuracy and targeting capability. The technological legacy of proximity fuses extended into Cold War military development, as both American and Soviet forces recognized the strategic importance of electronic warfare capabilities and precision-guided munitions systems. The miniaturization techniques developed for VT fuses became foundational technologies for guided missile systems, satellite navigation, and eventually, modern smart weapons that dominate BRIA. Contemporary military arsenals. Dorothy Chen's post-war career included pioneering work in consumer electronics development, applying manufacturing techniques learned during proximity fuse production to television and radio systems that brought electronic entertainment into American homes throughout the 1950s. Chen's experience managing large-scale precision manufacturing operations proved invaluable in establishing quality control procedures that became industry standards for electronic component production. The security measures surrounding proximity fuse development established precedents for protecting sensitive military technologies during the Cold War period, including compartmentalized research programs and industrial security protocols that prevented technology transfer to potential adversaries. The organizational models created for VT fuse development influenced subsequent major military research programs, including radar improvement, jet engine development, and eventually, space exploration initiatives. Professor Weber's post-war analysis of captured American proximity fuses provided valuable insights for German electronics industry reconstruction, contributing to the nation's eventual technological recovery while demonstrating the decisive importance of maintaining scientific and industrial capabilities during national emergencies. Weber's research highlighted critical gaps in German wartime technology policy that had prevented effective responses to Allied innovations. The proximity fuse program demonstrated that democratic societies could mobilize scientific resources effectively when facing existential threats. creating collaborative relationships between academic researchers, government agencies, and private industry that became models for post-war science policy development. The success of VT fuse development influenced establishment of permanent federal research institutions, including the National Science Foundation, and expanded military research programs. Admiral Spruance's tactical reports documented how proximity-fused defensive systems enabled American naval forces to operate with unprecedented boldness in contested waters, maintaining continuous pressure on Japanese positions while minimizing losses from enemy air attacks. Spruance's analysis influenced post-war naval doctrine development and ship design principles that emphasized technological superiority over numerical advantages. The human cost of proximity fuse effectiveness included enormous casualties among German and Japanese forces who lacked comparable defensive technologies, raising questions about technological asymmetries in modern warfare and their implications for international humanitarian law. The weapon's precision and lethality exceeded traditional concepts of proportionality, while demonstrating how scientific advantages could provide decisive military superiority. Captain Hoffman's recovery from wounds sustained during proximity-fused artillery attacks required extensive medical treatment that highlighted the severe nature of fragment injuries caused by overhead explosions, leading to improvements in battlefield medical procedures and protective equipment design. Hoffman's medical records contributed to understanding of wound patterns and treatment protocols that influenced military medical development throughout the post-war period. The economic impact of proximity fuse production created thousands of high-skilled manufacturing jobs while establishing American electronics industry leadership that continued throughout the post-war boom period, demonstrating how military research investments could generate broader economic benefits that extended far beyond immediate defense applications. The technological capabilities developed for VT fuse manufacturing became competitive advantages in consumer electronics markets. Major Kane's artillery battery became a testing ground for advanced proximity fuse applications, including experimental shells designed for specific target types and battlefield conditions that required specialized electronic configurations and detonation patterns. Kane's tactical innovations influenced artillery doctrine development while providing valuable feedback for continued VT fuse improvement programs throughout the war and post-war period. The intelligence lessons learned from proximity fuse security measures influenced Cold War counterintelligence procedures and BRAL, technology protection protocols that prevented Soviet acquisition of sensitive American military technologies during the early nuclear age. The compartmentalized research approach developed for VT fuse programs became standard practice for protecting classified military research from foreign espionage attempts. General Galland's post-war aviation career included extensive analysis of how proximity-fused weapons had altered aerial combat dynamics, contributing to development of jet fighter tactics and electronic countermeasure systems that became essential components of Cold War military aviation. Galland's insights about technological warfare influenced NATO tactical doctrine and pilot training programs throughout the 1950s and 60s. The scientific methodology developed for proximity fuse research established collaborative research techniques that became standard practice in major technology development programs, including systematic testing procedures, interdisciplinary team coordination, and accelerated development timelines that maximized innovation while maintaining quality standards. These organizational innovations influenced post-war industrial research and development practices across multiple sectors. Lieutenant Weber's detailed combat reports provided comprehensive documentation of pilot psychology when facing technologically superior opponents, contributing to understanding of how technological asymmetries influence military morale and tactical effectiveness. Weber's testimony became valuable case study material for military psychology research and pilot training programs designed to prepare aircrews for technological warfare scenarios. The proximity fuse represented the culmination of American scientific and industrial mobilization during World War II, demonstrating that democratic societies could achieve technological breakthroughs that provided decisive military advantages when national survival was at stake. The program's success vindicated investments in basic scientific research while establishing technological innovation as an essential component of national security strategy that influenced American defense policy throughout the Cold War and beyond. Dr. Gottwald's detailed technical analysis of captured proximity fuses provided German industry with insights into advanced manufacturing techniques and miniaturization, technologies that contributed to post-war economic recovery while highlighting the strategic importance of maintaining scientific research capabilities during peacetime. Gottwald's work influenced German technology policy and industrial development strategies throughout the Reconstruction period. The ripple effects of proximity fuse technology extended far beyond immediate battlefield applications, fundamentally reshaping how military strategists conceived modern warfare while establishing technological precedents that would influence conflicts for decades to come. The success of VT fuses demonstrated that scientific innovation could provide decisive advantages that traditional military doctrine could not counter, forcing a complete reevaluation of defense spending priorities and research investment strategies. Colonel James MacArthur, serving as a strategic analyst with the War Department, recognized that proximity fuses represented merely the beginning of an electronic warfare revolution that would transform MAGS military operations across all domains. MacArthur's comprehensive study, completed in early 1945, predicted that future conflicts would be dominated by nations possessing superior electronic capabilities rather than those relying on conventional weapons systems or numerical advantages. MacArthur's analysis proved prophetic, as post-war military development focused increasingly on sophisticated guidance systems, radar technology, and electronic countermeasures that drew directly from innovations pioneered during proximity fuse development. The organizational structures created for VT fuse research became templates for Cold War military research programs, including guided missile development, satellite technology, and eventually, the space program itself. The human drama behind proximity fuse development included countless personal sacrifices made by researchers, engineers, and production workers who dedicated years of their lives to creating weapons they hoped would end the war more quickly. Dr. Margaret Foster, a mathematician recruited from Princeton to develop trajectory calculations for VT fuse testing, worked 18-hour days for 3 years straight while maintaining absolute rest. Secrecy about her contributions to the war effort. Foster's mathematical models proved essential for optimizing proximity fuse sensitivity patterns and detonation timing, requiring complex calculations that accounted for aircraft speed variations, altitude changes, and atmospheric conditions that affected radio wave propagation. Her work demanded unprecedented precision in mathematical modeling, while operating under time pressures that left no room for errors or extended verification procedures. The personal cost of this dedication became apparent only after the war ended, as Foster and her colleagues struggled to readjust to civilian life after years of intense, classified work that they could not discuss with family members, or friends. Many VT fuse researchers experienced what would later be recognized as symptoms of chronic stress and social isolation caused by prolonged involvement in highly classified projects. Meanwhile, in the field, American combat units were discovering new applications for proximity-fused weapons that had never been anticipated during original development phases. Lieutenant Colonel Robert Hayes, commanding an armored regiment during the final push into Germany, began using VT-fused artillery shells against German defensive positions in urban environments where traditional artillery proved ineffective due to building structures that provided excellent protection against conventional explosions. Hayes discovered that proximity-fused shells could be adjusted to detonate at specific heights above city streets, creating fragment patterns that penetrated into buildings through windows and doorways while minimizing structural damage that might impede subsequent military operations. This tactical innovation proved particularly effective during the Battle of Cologne, where German forces had fortified cathedral areas and historic buildings that American commanders preferred to preserve if possible. The ethical implications of using proximity fuses in urban combat generated intense debate among military leadership, as the weapon's effectiveness against civilian areas raised questions about proportionality and discrimination that had not been fully considered during original development. However, The weapon's precision actually reduced collateral damage in many situations by allowing more targeted attacks that achieved military objectives without requiring massive bombardments that would have destroyed entire city blocks. German civilians caught in these urban battles provided first-hand accounts of proximity-fused artillery that demonstrated the weapon's psychological impact extended far beyond military targets. Anna Zimmerman, a nurse working in Cologne during the American assault, described shells that seemed to explode with supernatural timing, always at precisely the right moment to achieve maximum effect against German defensive positions, while minimizing harm to non-combatants seeking shelter in basement areas. Zimmerman's diary, discovered decades after the war, documented the profound fear experienced by civilian populations when exposed to weapons that seemed to possess intelligence and targeting capability beyond human comprehension. Her accounts described the gradual breakdown of civilian morale as residents realized that traditional air raid shelters and defensive measures provided little protection against American artillery that could apparently see through walls and terrain features. The intelligence war surrounding proximity fuses intensified during the final months of the European campaign, as German scientific services made desperate attempts to capture intact American VT fuses for reverse engineering purposes. SS Oberführer Heinrich Müller organized specialized commando units tasked with raiding American ammunition dumps and artillery positions to obtain proximity fuse samples before they could be used in combat. Müller's operations achieved limited success, recovering several damaged VT fuses from crash sites and battlefield locations, but the devices proved too sophisticated for German scientists to analyze effectively within available timeframes. The miniaturization techniques and electronic components required manufacturing capabilities that German industry simply could not provide under wartime conditions, making effective countermeasure development virtually impossible. The captured fuses did provide German forces with tactical intelligence about proximity fuse operational characteristics, including radio frequencies, detection ranges, and sensitivity patterns that could be exploited through careful tactical planning. German fighter pilots began using this information to develop evasive maneuvers and attack patterns designed to minimize exposure to VT-fused anti-aircraft fire, achieving marginal improvements in barrage survival rates. However, these tactical adaptations came at enormous cost in terms of operational effectiveness, as German aircraft were forced to use flight patterns that reduced their ability to engage Allied targets effectively while requiring extensive pilot training programs that Germany could not afford given critical shortages of fuel, aircraft, and experienced instructors. The proximity fuse had forced German forces into tactical positions that neutralized many of their remaining advantages through technological rather than military pressure. Dr. Tuve's research team continued developing improved proximity fuse variants throughout 1945, incorporating lessons learned from combat experience while preparing for anticipated operations against Japanese home islands that would require VT fuses optimized for different tactical scenarios. These advanced models included adjustable sensitivity settings, improved weather resistance, and enhanced electronic countermeasure protection that made them even more effective against enemy adaptive measures. The planned invasion of Japan, codenamed Operation Downfall, was expected to require unprecedented quantities of proximity-fused ammunition for both naval gunfire support and ground artillery operations against heavily fortified Japanese positions. Military planners estimated that VT fuses would be essential for achieving acceptable casualty rates among American forces while overcoming Japanese defensive advantages provided by terrain, familiarity, and prepared positions. However, the atomic bombings of Hiroshima and Nagasaki eliminated the need for invasion operations while demonstrating that American technological superiority extended far beyond proximity fuses to include weapons of unimaginable destructive power. The Japanese surrender in August 1945 occurred just as proximity fuse production reached peak efficiency levels that would have supported the largest military operation in human history. The sudden end of the war created immediate challenges for proximity fuse production facilities, as government contracts were cancelled, and thousands of workers faced unemployment despite their crucial BEA contributions to Allied victory. Dorothy Chen found herself managing plant closures and worker transitions while maintaining security restrictions that prevented public recognition of VT-Fuse achievements or worker contributions to the BEA war effort. The post-war transition proved particularly difficult for researchers and engineers who had devoted years to proximity fuse development, while operating under conditions of absolute secrecy that prevented them from discussing their accomplishments with potential civilian employers. Dr. Foster struggled to find academic positions that utilized her mathematical expertise without revealing her classified wartime contributions, ultimately accepting teaching positions far below her qualifications and experience level. The declassification process for proximity fuse technology extended over several years, as military authorities attempted to balance public recognition of scientific achievements against security requirements that protected American technological advantages during the emerging Cold War confrontation with the Soviet Union. The gradual release of information about VT fuse development allowed belated recognition of scientific contributions while maintaining secrecy about specific technical details that remained militarily sensitive. Commander Richardson's post-war naval career included extensive work developing advanced anti-aircraft systems that incorporated lessons learned from proximity fuse combat experience, contributing to guided missile development programs that would become essential components of Cold War naval defenses. Richardson's expertise in VT fuse tactical applications made him a valuable consultant for NATO naval cooperation programs that shared defensive technologies among allied nations while preventing technology transfer to potential adversaries. The industrial legacy of proximity fuse production influenced American manufacturing capabilities throughout the post-war economic boom, as companies like General Electric applied precision manufacturing techniques developed for VT fuses to civilian electronics production, including television sets, radio equipment, and, eventually, computer components. The quality control procedures established for proximity fuse manufacturing became industry standards that contributed to American technological leadership in consumer electronics markets. Japanese military analysis of American proximity fuse effectiveness provided valuable lessons for post-war self-defense force development, as Japanese strategists recognized that future conflicts would require sophisticated electronic warfare capabilities rather than traditional emphasis on fighting spirit and tactical expertise. The devastating effectiveness of VT-fused weapons against Japanese forces demonstrated that technological innovation could provide decisive advantages that could not be overcome through conventional military virtues. Captain Yamamoto's survival of the war, despite commanding kamikaze operations against proximity-fused defenses, provided unique insights into how technological asymmetries affected military psychology and tactical decision-making under extreme conditions. Yamamoto's post-war writings emphasized that facing technologically superior opponents required fundamental changes in military doctrine and training rather than mere tactical adaptations or improved conventional weapons. The scientific methodology developed for proximity fuse research influenced post-war industrial research and development practices across multiple sectors, including pharmaceutical development, aerospace engineering, and eventually computer technology that drew directly from miniaturization techniques pioneered during VT fuse production. The collaborative research models established during wartime continued functioning during peacetime, creating permanent institutional relationships between academic researchers, government agencies, and private industry. Sergeant Kruger's detailed combat memoirs provided German military historians with comprehensive documentation of how proximity-fused weapons affected infantry tactics and unit cohesion, contributing to understanding of technological warfare that influenced NATO tactical doctrine development throughout the Cold War period. Kruger's accounts of facing apparently supernatural weapons accuracy helped military psychologists develop training programs designed to prepare soldiers for technological warfare scenarios. The economic impact of proximity fuse development extended far beyond immediate wartime expenditures, creating technological capabilities and manufacturing expertise that generated enormous economic returns throughout the post-war boom period. The billion-dollar investment in VT fuse research and production proved to be one of the most successful technology development programs in American history, generating economic benefits that exceeded original costs by orders of magnitude. Major Kane's artillery innovations using proximity-fused shells influenced post-war field artillery doctrine development while contributing to guided munitions programs that became standard DPN components of Cold War military arsenals. Kane's tactical reports documenting VT fuse effectiveness against various target types provided valuable data for weapons system development and training programs that prepared American forces for potential future conflicts requiring technological superiority. The counterintelligence lessons learned from protecting proximity fuse technology established security procedures that became templates for Cold War classified research programs, including compartmentalized information access, industrial security protocols, and personnel screening procedures that prevented technology transfer to potential adversaries. These organizational innovations proved essential for maintaining American technological advantages during subsequent confrontations with Soviet intelligence services. Professor Weber's analysis of captured American proximity fuses contributed to German electronics industry reconstruction while highlighting critical importance of maintaining scientific research capabilities during peacetime to prevent technological gaps that could prove decisive during future conflicts. Weber's work influenced German technology policy and industrial development strategies that emphasized scientific education and research investment as essential components of national security. Lieutenant Weber's detailed pilot reports provided comprehensive documentation of aircrew psychology when facing technologically superior defensive systems, contributing to understanding of how technological warfare affected military effectiveness and unit morale under combat conditions. Weber's testimony became valuable case study material for pilot training programs and tactical doctrine development that prepared aircrews for electronic warfare environments. The strategic implications of proximity fuse technology extended beyond immediate military applications to influence Cold War defense policy and international relations. As nations recognized that technological superiority could provide decisive advantages in future conflicts, while requiring enormous investments in scientific research and industrial capabilities. The VT fuse demonstrated that democratic societies could mobilize scientific resources effectively when facing existential threats, creating collaborative models that influence subsequent major research programs. Dr. Gottwald's technical reports on American proximity fuses provided valuable intelligence for post-war German technology development, while demonstrating the decisive importance of industrial capabilities and scientific infrastructure in modern warfare. Gottwald's analysis influenced European technology cooperation programs and research investment strategies that emphasized maintaining competitive capabilities in advanced electronics and precision manufacturing. The humanitarian implications of proximity fuse effectiveness included both positive and negative consequences. As the weapons contributed to shortened conflict duration while inflicting enormous casualties on forces lacking comparable defensive technologies, the precision and lethality of VT-fused weapons raised questions about technological asymmetries in warfare and their implications for international humanitarian law that continue influencing modern military ethics discussions. General Manteufel's tactical analysis of facing proximity-fused artillery provided German military leadership with comprehensive understanding of how advanced weapon systems could neutralize traditional tactical advantages, contributing to post-war military doctrine development that emphasized technological innovation as essential for maintaining defensive capabilities against potential adversaries equipped with superior weapon systems. The educational legacy of proximity fuse development influenced American science and engineering programs throughout the post-war period. As universities expanded electronics and physics curricula to meet demand for skilled technicians and researchers capable of working with sophisticated military and civilian technologies. The wartime collaboration between academic institutions and government agencies created permanent relationships that continued supporting advanced research programs during peacetime. Admiral Spruance's strategic reports documenting proximity fuse effectiveness in Pacific operations influenced post-war naval doctrine development and fleet composition decisions that emphasized technological superiority over numerical advantages in ship construction and crew training programs. Spruance's analysis contributed to understanding of how advanced weapons systems could provide decisive tactical advantages that justified enormous research and development investments. The international implications of American proximity fuse superiority influenced post-war alliance relationships and technology sharing, agreements that balanced military cooperation against security requirements for protecting sensitive technologies from potential adversaries. The success of VT fuse development demonstrated that technological collaboration among democratic nations could provide collective security advantages while maintaining individual national bashna interests. Captain Hoffman's medical recovery from proximity fuse injuries contributed to advances in trauma medicine and protective equipment development that benefited both military and civilian medical practice. Throughout the post-war period, Hoffman's case studies provided valuable data for understanding fragment injury patterns and treatment protocols that influenced emergency medicine development and battlefield medical procedures. The declassification of proximity fuse technology in the late 1940s finally allowed public recognition of one of the war's most significant but hidden scientific achievements, revealing to the world how a small team of American researchers had fundamentally altered the course of military history through their innovative electronic warfare breakthrough. The public revelation generated enormous interest in the scientific community while raising important questions about the relationship between academic research and military applications during national BS emergencies. Dr. Vannevar Bush, who had coordinated wartime scientific research as director of the Office of Scientific Research and Development, used the proximity fuse program as a prime example of how democratic societies could mobilize intellectual resources effectively when facing existential threats. Bush's post-war writings emphasized that VT fuse development demonstrated the crucial importance of maintaining strong peacetime scientific institutions that could rapidly transition to military applications when national security required such transformation. The revelation of proximity fuse capabilities also generated significant interest among former German military personnel, many of whom had spent years wondering how American forces had achieved such dramatic improvements in weapons effectiveness during the final phases of the war. Former Wehrmacht officers interviewed by Allied intelligence services expressed amazement at the sophistication of American BA electronic technology while acknowledging that they had been fighting an enemy whose scientific capabilities far exceeded their understanding. General Heinz Guderian, Germany's leading tank warfare expert, admitted in post-war interviews that German military leadership had consistently underestimated American technological capabilities, while overemphasizing traditional military virtues such as tactical skill and fighting spirit. Guderian's analysis suggested that Germany's defeat resulted as much from scientific inferiority as from resource shortages or strategic miscalculations, highlighting the decisive importance of maintaining technological superiority in modern warfare. The broader implications of proximity fuse development influenced American science policy throughout the Cold War period, as political leaders recognized that scientific research investment could provide national security advantages that justified enormous expenditures on basic research programs. The National Science Foundation, established in 1950, drew directly from organizational models developed during VT fuse research, while incorporating lessons learned about managing large-scale scientific collaboration between academic institutions and government agencies. Meanwhile, Soviet intelligence services had been conducting extensive investigations into American proximity fuse technology since the war's end, attempting to understand and replicate the scientific breakthroughs that had provided Allied forces with such decisive tactical advantages. Soviet efforts proved largely unsuccessful due to fundamental gaps in electronics manufacturing capabilities and miniaturization, techniques that required industrial infrastructure investments far beyond available resources during the immediate post-war reconstruction period. Colonel Sergei Volkov, leading Soviet electronic warfare research programs, submitted comprehensive reports to Moscow describing American VT fuse technology as representing at least a 5-year advantage in electronics development over existing Soviet capabilities. Volkov's analysis warned that American technological superiority could provide decisive advantages in future conflicts unless the Soviet Union invested heavily in scientific research and advanced manufacturing capabilities comparable to those demonstrated during proximity fuse development. The personnel who had contributed to proximity fuse development found their wartime experience increasingly valuable as Cold War tensions escalated, and both military and civilian organizations sought expertise in advanced electronics and precision manufacturing. Dr. Foster eventually joined the nascent computer industry, applying mathematical modeling techniques developed for VT fuse trajectory calculations to early programming and systems analysis challenges that became foundational elements of the emerging Bach information technology revolution. Dorothy Chen's manufacturing expertise proved invaluable in establishing quality control procedures for emerging consumer electronics industries. As companies like RCA and Westinghouse sought to commercialize television and radio technologies that drew directly from innovations pioneered during military electronics development, Chen's experience managing large-scale precision manufacturing operations under extreme time pressures became a template for industrial management practices throughout the post-war economic boom. The medical implications of proximity fuse injuries continued influencing trauma treatment development throughout the 1950s. As battlefield physicians applied lessons learned from treating fragment wounds to civilian emergency medicine practices. Dr. Patricia Williams, who had treated proximity fuse casualties during European operations, pioneered surgical techniques for removing small metal fragments that became standard procedures in civilian hospitals dealing with industrial accidents and automotive injuries. Williams' research on fragment injury patterns contributed to improved protective equipment design for both military and civilian applications, including better helmet configurations, body armor materials, and workplace safety equipment that reduced injury severity in situations involving high-velocity metal fragments. Her work demonstrated how military medical experience could generate broader benefits for civilian healthcare systems while advancing understanding of trauma treatment protocols. The psychological impact of facing proximity-fused weapons continued generating research interest among military psychiatrists studying combat stress and technological warfare effects on soldier psychology. Dr. Robert Stone, who had interviewed hundreds of German prisoners during and after the war, documented consistent patterns of demoralization and helplessness among enemy forces who had been subjected to VTF-fused artillery barrages or anti-aircraft fire. Stone's research revealed that proximity fuses created psychological effects beyond their immediate tactical impact, as enemy soldiers developed learned helplessness when facing weapons that seemed to possess supernatural accuracy and intelligence. These psychological studies influenced military training programs designed to prepare American forces for potential future conflicts involving technologically advanced adversaries, while contributing to understanding of how weapons technology could affect unit morale and combat effectiveness. The environmental implications of large-scale proximity fuse production included pioneering developments in electronic waste management and materials recycling, as General Electric facilities had to dispose of thousands of defective vacuum tubes and electronic components while maintaining security restrictions that prevented conventional waste disposal methods. The company developed specialized recycling procedures that recovered valuable materials while ensuring that sensitive technological information could not be reconstructed from discarded components. These environmental management innovations became templates for Cold War defense industry practices that balanced security requirements against environmental responsibility, contributing to early development of industrial recycling programs and waste reduction techniques that influenced broader manufacturing practices throughout American industry during the post-war period. The international technology transfer implications of proximity fuse development continued influencing American foreign policy throughout the 1950s. As Allied nations sought access to VT fuse technology, while American authorities attempted to balance military cooperation against security requirements for protecting sensitive information. The establishment of NATO created frameworks for selective technology sharing that allowed certain allied nations to receive proximity fuse capabilities while maintaining restrictions that prevented DALA technology transfer to potential adversaries. British and Canadian forces received full access to American proximity fuse technology as reward for their wartime scientific collaboration and continued alliance relationships, while other NATO partners received limited access based on strategic importance and security considerations. These technology sharing arrangements established precedents for Cold War military cooperation programs that balanced collective security requirements against national security interests in protecting CREF. Advanced weapons technologies. The educational impact of proximity fuse development extended beyond immediate technical applications to influence American attitudes toward science and technology education throughout the post-war period. The success of VT fuse development demonstrated that scientific research could provide practical solutions to critical national problems while generating enormous economic benefits that justified BCRE. Educational investments in mathematics, physics, and engineering programs. Universities across the country expanded their electronics and engineering curricula to meet growing demand for skilled technicians and researchers capable of working with sophisticated military and civilian technologies developed during wartime research programs. The GI Bill provided funding for thousands of veterans to pursue advanced education in scientific fields, creating a generation of highly trained researchers and engineers who contributed to American technological leadership throughout the Cold War period. The Proximity Fuse program also established important precedents for government-industry collaboration in advanced technology development, creating organizational models that influenced subsequent major research programs, including jet engine development, radar improvement, guided missile systems, and eventually the space program itself. The successful integration of academic research, government funding, and private industry capabilities demonstrated that democratic societies could achieve technological breakthroughs comparable to those achieved by totalitarian regimes through centralized planning and resource allocation. Commander Richardson's continued work with advanced naval weapons systems contributed to development of guided missile technologies that became essential components of Cold War naval defenses, including surface-to-air missile systems that drew directly from proximity fuse innovations while incorporating improved guidance and target acquisition capabilities. Richardson's expertise in VT fuse combat applications made him a valuable consultant for international naval cooperation programs that shared defensive technologies among allied nations. The legacy of proximity fuse manufacturing extended into emerging aerospace industries, as companies like Boeing and Lockheed applied precision manufacturing techniques developed for VT fuse production to aircraft and missile system development throughout the 1950s and 60s. The quality control procedures and miniaturization capabilities established during wartime electronics production became competitive advantages that contributed to American leadership in commercial aviation and space exploration technologies. Major Kane's continued military service included extensive work developing advanced artillery systems that incorporated lessons learned from proximity fuse combat experience, contributing to guided munitions programs that revolutionized ground warfare capabilities throughout the Cold War period. Kane's tactical innovations using VT-fused shells influenced field artillery doctrine development while providing valuable feedback for weapon system improvement programs that maintained American brand technological superiority over potential adversaries. The proximity fuse story concluded not with the war's end, but with the beginning of a technological revolution that transformed both military and civilian society throughout the remainder of the 20th century and beyond. The small team of scientists working in Maryland laboratories had created more than just a better weapons system. They had demonstrated the decisive importance of scientific innovation in modern competition, while establishing technological development as an essential component of national strategy that would define American leadership in the post-war world. In the end, the proximity fuse stood as testament to the power of human ingenuity and scientific collaboration when directed toward solving critical problems, proving that small teams of dedicated researchers could create technologies that changed the course of history while establishing precedents for post-war technological development that continue benefiting society today. The revolution that began in Maryland laboratories had transformed warfare forever, ensuring that future conflicts would be decided as much by scientific capability as by traditional military virtues, and establishing technological innovation as an essential component of national security strategy that would define the remainder of the 20th century and beyond.